In our previous lecture, we introduced the definitions of stability and asymptotic stability of an equilibrium point, and without loss of generality, we took the equilibrium point to be the origin of an autonomous system, a general nonlinear system. And qualitatively speaking, the origin we call the origin a stable equilibrium point if you start close enough to the origin, you stay, or the trajectories stay close enough to the origin, okay? Or more precisely, for any epsilon that will give me a positive number, I can always find, if I can always find delta, so another positive number, such that provided that I start the system in the delta neighborhood of the origin, all the trajectory in the future stays always in the epsilon neighborhood. Okay, it never leaves the epsilon border. And as for asymptotic stability, on top of stability, we also require that the solutions, provided that they start close enough to the origin, converge to the origin as time goes on. Now, the important question of checking stability, that is, given a nonlinear system with an equilibrium point at the origin, how can we check whether the origin is stable or not, is an important question. Okay? And one answer to that question could be, well, just directly apply the definition of stability or asymptotic stability, but that's not a feasible solution because in general we don't know how to obtain explicitly the solutions of a nonlinear system, and the definition is in terms of the solutions. Therefore, if you don't know the solutions, if you cannot write down the solutions, then you cannot apply the definition to check whether the origin is stable or not. Okay? But then we talked about the pendulum, and we there saw that we don't actually have to know the explicit solution in order to be able to check that epsilon delta condition. Okay, what we did there was we studied the total energy of the pendulum, okay, which is a positive function. It's only zero at the origin, and then how we studied it was we computed its time derivative along the solutions of the system. And we have shown that the time derivative was never positive, okay? And from that non-positivity, okay, or negativity of the derivative of the energy function, we deduced simply that the origin has to be stable. Now, that is a very valuable idea, using a positive function and looking at its time derivative to determine the stability properties of an equilibrium of a system. Okay? So that idea was extended to the general case of arbitrary systems by Alexander Lyapunov, okay, the Russian scientist, and we therefore have arguably the most important tool in the stability theory of dynamical systems, which is Lyapunov's stability theory. In this lecture, we will state that theorem, and we will talk about its proof. Stability theorem. Okay. It has many variations. Okay, we're considering a general case, but even more general statements are possible. But as for the main idea, it's always the same in all its versions. Okay, so this is a general enough of a version, and therefore we're going to study that. So let x equals 0, the origin B, an equilibrium of the system denoted by x that equals f of x, and suppose that f is continuous. Okay, and also we're implicitly assume that the solutions exist for all future times uniquely. Okay. And that this D denote a subset of Rn, okay, where f is, where x is in Rn, okay. B, an open subset containing the origin. Okay. Then suppose that we constructed, or we are given the following function that's defined on D. Let V that maps points from this subset to the real line be a continuously differentiable function satisfying the following conditions. Okay, the first condition is positive definiteness. It's 0 at 0, so this is the vector 0 because its arguments are coming from a subset of Rn, and this is the scalar 0 because it maps everything to the real line. 0 at 0, and it's strictly positive elsewhere. In D, take away 0. Okay, let's call this condition condition 1. And as for its time derivative, that x is never positive in D. Okay. And let's call this 2. And also remember what V dot meant. Okay. So V dot, by V dot, we mean this inner product gradient of V, okay, with the right hand side of the system. Okay. Then, under those two conditions, we have the stability of the origin. Is stable. Okay. Furthermore, if you can strengthen this condition into that V dot is strictly negative at all points in D except the origin, then you have asymptotic stability of the origin. Moreover, if V dot x is strictly negative in D, take away the origin, let's call this 3, then our equilibrium point is asymptotically stable. Is asymptotically stable. Okay. Now we will try to establish this claim. Let's first talk about stability, and in the second half we can extend our analysis to asymptotic stability case. Stability under the conditions 1 and 2. Now, definition of stability of equilibrium point was the following. You give me any epsilon, okay, a positive number. Then if I can find a delta, okay, another positive number, such that provided that the initial condition, the normal initial condition is no greater than delta, if all the future values of the norm of the solution is less than or equal to epsilon, then the origin is stable. Okay, so let us be given that epsilon in that definition. Okay. Now, given epsilon greater than 0, we will now try to figure out the delta. Okay. Such that if the norm of the initial condition is less than or equal to delta, then the norm of the future values of the solution will always be less than or equal to epsilon. Now, given this epsilon, it's any epsilon, okay, arbitrary. What we do is we choose another positive number, strictly less than epsilon, such that the so-called R bowl, denoted by B sub R, x in Rn, set of all points whose norm or whose distance to the origin is no greater than R. Okay, so that's the notation that we introduced. This is called R bowl. Okay, this is the origin, and then if this is the radius R, by R bowl we mean the set of points within that disk. Of course, the word disk is reserved for the plane, and we're in Rn now, so in R3 to be a sphere, and in R4 be hypersphere, something like that. But all those fancy names are replaced by this word bowl. Okay. Is contained in D. Okay. Now let me squeeze here a very primitive picture, so that we will keep track of the sets that we use as we go along. So let this be D, okay, an open subset. And then somewhere inside D, we have the inner point, the origin, of whose stability we're now studying. And then, what we do now here is, given an epsilon, what we do is we choose a bowl, okay, an R bowl, that contains an R bowl that's within D. It's not that large, and also it's smaller than the radius R is smaller than the epsilon that we've given, and we can always find such an R bowl. Okay, so this is our BR. Okay, it's contained in D. Okay, and then let us define this positive number alpha. Okay, let alpha be the minimum value of, or minimum value attained by V of x, and the set that we perform the minimization is the set of points whose distance to the origin is exactly R. So this is on the plane, it's just a circle with radius R. Okay, so that circle is closed and bounded set is a continuous function. Therefore, this minimization has a solution, and that solution, that number, that real number, has to be positive because V of x is 0 only at 0. Elsewhere, it's strictly positive. Okay, so that's alpha. Then alpha must be a positive constant by condition 1. Okay, satisfied by V. Then what? And then choose beta that's positive but strictly smaller than alpha here, and define the following set in terms of the so-called Lyapunov function V of x. Define omega sub beta as the intersection of R and set of points that are less than or equal to beta. Okay? For lethally autonomous function of x. Note that this set is a subset of both the R ball and that Vx less than or equal to beta set because of the definition of intersection. Note that omega beta is a subset of VR, which will be useful later on. Now, this omega beta is contained by VR because it's constructed by VR intersected by something. Therefore, in our picture, it has to be somewhere within VR. Okay, so roughly, let's put it somewhere here, and this is our omega beta. Okay. Now, here is our first claim, which is that if the initial condition, if you pick the initial condition such that it's inside the set that we constructed here, omega beta, then for all future times it will remain in omega beta. Okay? And now we're going to achieve that using the properties or the conditions satisfied by the development function. X initial condition belonging to the set that we construct, omega beta, implies for all future times the solution remains in that set omega beta. Not that when such property is satisfied, we say that set omega beta is forward invariant with respect to the system X that goes f of x for all t greater than or equal to 0. Now, this may be obvious to some of you, but it's not that obvious, so we have to actually demonstrate that. Okay, so we have to prove that. Why this claim has a chance to be true. This is why we're going to prove that claim by contradiction. That is, we will suppose that this claim is false, okay, and then we'll figure out the consequences, and if those consequences are contradictory to what has been assumed, then we will have proven the claim. So the first sentence, therefore, is suppose not. Okay. That is, for some initial condition in this, starting from in this set omega beta, the solution that starts from that initial condition at some point in time, let's call it t1, leaves this set, okay, omega beta. So that's what has to be true if this claim is false. Okay, that is, for some t1 and for some initial condition x0, xt1 does not belong to omega beta, okay, for some t1 greater than 0. Okay. Now, this set is constructed as intersection of two sets. Therefore, in some point in time, if solution doesn't belong to this set, it means it either does not belong to this set or does not belong to that set. If it does belong to both of the sets, it must also belong to the intersection. Therefore, it belongs to omega beta. Hence, if something doesn't belong to omega beta, it means that that thing at least has to be a non-member of either this guy or that guy. Okay. So, by simple reasoning, either of the following must hold. Okay. Either xt1 does not belong to the R ball, or Vxt1 strictly greater than beta. That is, it does not belong to this set. V of x is equal to beta. Okay, now what we're going to do is we're going to consider each of these cases separately, and we're going to see that both of them or neither of them can be true, and as a result, by contradiction, we will have proven our claim. Okay, so consider each case separately. Okay, the first case is that x of t1 does not belong to BR. Okay, suppose that this is true. This means what? Okay, this means what? So we start in x rho is in omega beta. It's in omega beta means it's in BR. Okay, and then okay, it's in BR, and at some point later on, it's not in BR. Okay, so that means in some point in time, it has to cross the border of that that ball, R ball. Okay, so at some point, its distance to the origin must be exactly R. Okay, means there exists a time, okay, t2 less or equal to t1, such that x t is strictly less than r, okay, for t in 0 to t2, and x t2 equals r. So basically, we're considering the first time that the solution crosses or intersects the border of the R ball. Okay. Note that we cannot start at the border. The initial condition cannot be at the border. Okay, so initial condition must be that it's the distance of it is less than or equal to R, because if we're on the border, then V of x0 have to be larger than R. Okay, but V of x is less than or equal to beta, and beta is chosen to be smaller than R. So initially we start in the interior of the R ball, and then if this condition is satisfied, so that means at some point in time we're crossing to the outside, to the other side, through the border. Okay. Therefore, Vxt2 must be greater or equal to alpha, because alpha is defined as the minimum value V of x attains where the minimization is performed through this set. Okay, norm of x equals r, and norm of x at t2 equals r. Okay, then you pass this particular point xt2 through v. Okay, and the value that it attains cannot be any smaller than alpha by definition of alpha. Okay, so it's either alpha or something larger. But for t in 0 to t2, what we have is x of t belongs to the R ball. So x of t belongs to R ball means that it also belongs to D, because R ball is contained in D. Okay? And if x of t is in D, therefore the condition for the derivative of the Lyapunov function is valid. That is, the time derivative is never positive. Okay, hence v dot is less than or equal to 0 by condition 2. Now, since v of x of 0 is less than or equal to beta, we have what? Okay. Now, initial condition starts in omega beta. Omega beta is a subset of Vx less than or equal equal to beta. Therefore, initial v of x0 must be less than or equal to beta. Okay, so that's the initial condition. And what else? For all this time, from 0 to t2, v cannot increase. Okay, therefore, throughout this interval, v of x of t must remain below beta. So that means at time t equals t2, v of x of t2 must be less than or equal to beta. Okay, so we have v of x of t2 is less than or equal to beta. Okay, so what we obtained, let's check, we obtained that v is greater than or equal to alpha, and also v is less than or equal to beta. So that means beta is greater than or equal to alpha. Okay. Then follows the contradiction. Beta greater than or equal to alpha. Why is it a contradiction? It's because we have chosen beta such that it's strictly smaller than alpha. But here, what we obtained is beta is equal to or larger than alpha. So that's why we have a contradiction. We have chosen beta strictly less than alpha. Okay, therefore, this cannot be true. How about other possibility? V of xt1 greater than beta. Now we will rule out that possibility quite fast, and which will, as a result, give us the claim. V of x of t1 greater than beta. So we've just established here, okay, that x of t remains in R for all future time. Okay, there does not exist any time t1 where the solution leaves the R. Therefore, solution must remain in R for all future times. If it remains in R for all future times, it remains in domain D for all future times, and as long as it remains in domain D, the subset D, V dot is never positive. V dot never positive means V cannot increase. V cannot increase means that we can never exceed beta, because beta is where we, beta of something smaller is where we started from. Okay, for all t greater than 0, therefore x of t remains in D for all t. Okay, hence by condition 2, V dot is never positive for all t for that particular solution. Then Vx0 less than or equal to beta, because x0 starts in omega beta, and by definition omega beta means that v of x is less than or equal to beta. Then this implies Vx of t less than or equal to beta for all times, okay, for all future times. This contradicts this. Okay, therefore, our claim here is correct. Okay, now let's return to the proof of the theorem. Okay, now v of x is continuous. Okay, so y assumption, and also it's 0 at 0. Okay, these two things mean that I can always find a delta that's small enough such that x close enough to the origin yields v of x is less than beta. Okay, directly from continuity plus the fact that it's 0 at 0. Hence, we can squeeze a delta ball around the origin. Okay. That delta ball, if we're in that delta ball, then it means that we're also satisfying Vx less than equal to beta. Well, that needs to be shown, in fact. Okay, let's show that. Now, that's how we have chosen our delta. Okay, once again, what we're trying to show is that we're given an epsilon. That was the very first thing that we started from. And then, after some step, we now come to this point that we choose a delta according to the following constraint. And we know that from continuity, and this fact, such delta always exists. Now, what remains to be shown is that this delta works for the epsilon that we're given, meaning that if the initial conditions stay in, start from the delta ball, then the solution never leave the epsilon ball. Okay. Now, then delta ball is a subset of set omega beta. Now, let's prove this also. Note that delta is less than r. All we have to show is this, because this set omega beta is defined as the intersection of b less than or equal to beta and the r ball okay. If we can show that delta is smaller than r, so that means b delta okay is a subset of dr, and also if x is in d delta, this condition is automatically satisfied, and therefore d delta would be a subset of omega beta. Okay. Delta r for otherwise, okay, suppose that is, if delta is greater than or equal to r, you would have the following contradiction. Beta greater than max x less than or equal to delta e of x. Okay. Now this is, in a sense, the definition of delta. We have chosen delta so that as long as the norm is less than or equal to delta, then b of x is less than or equal to beta. Okay, beta was there first, then before that beta we choose the delta. So this is sort of the definition, or it follows from the definition of delta. And then now we're considering the consequence of delta being larger than or equal to r. If delta were larger than or equal to r, then we could have the following. Min v of x less than, excuse me, equals r. Okay. Now, if delta is larger than or equal to r, then this subset of this set will be a superset of norm of x equals r. Okay, so this set of points defined by this contained in set of points defined by this, if this were true. Okay. And then the maximum value attained by V in some set clearly is larger than the minimum value of V attained by V in some subset of this set here. Okay, and then by definition, this minimization we compute it to equal alpha. Okay. Okay. And that would mean beta is greater than alpha. Beta greater than alpha, which is a contradiction because alpha was there first, and then once the alpha is given, we have chosen beta such that it's strictly smaller than alpha. Therefore, we would have such contradiction. So, therefore, hence, x in delta ball implies x in r ball, because delta is strictly smaller than r. And also by definition, u of x is less than or equal to beta, provided that the norm of x is less than or equal to delta. Okay. So if x satisfies this and that together, that's the very definition of omega beta. Okay. That means if x is in delta ball, it's automatically in omega beta. Therefore, this claim is also proven. Now, this claim, together with the claim that we have proven previously, will give us the stability of the origin. Now, we can write the following x0 in delta ball. Suppose that we have chosen our initial condition inside delta ball. Norm of x0 is less than or equal to delta. Then x0 belongs to omega beta, because omega beta is a superset of delta ball. And then using the previous claim, if you started omega beta, you always stay in omega beta. So omega beta was forward invariant. For all times. And omega beta is constructed such that it's intersection of something with R ball. That means x of t belongs to omega beta, means x of t belongs to R ball for all times. Okay. And finally, we call that R was chosen after we're given epsilon and it's strictly smaller than epsilon. Okay. So that means x of t belongs to epsilon ball 2, because epsilon is larger than R. That is, finally, norm of x initial condition, okay, less than or equal to delta implies x of t is always within epsilon ball. That is less than or equal to epsilon for all t and greater than or equal to 0. And that's the very definition of stability. Okay, you give me any epsilon, I can find a delta such that this implication is satisfied. Hence, x0 is stable, which we have proven under the conditions 1 and 2 satisfied by the Lyapunov function. The first one was positive definiteness, the second one was negative semi-definiteness of the time derivative. Okay, now let's move on to asymptotic stability. Asymptotic stability under conditions 1 and 3. Okay, 1 was positive definiteness, 3 was negative definiteness of the time derivative of the Lyapunov function. So what we need now is, so we already proven stability. On top of that, we have to show also attractivity. So what we need to do is we need to establish x of t converges to origin as most inferior. Okay. So we begin by the following claim. For each b, positive end strictly less than beta. Beta is what we have defined in the first part. There exists a finite time, capital T, such that norm of the initial condition less or equal to delta, or less than delta, implies v of x of t less or equal to b, provided that for all times larger than capital T. Okay, so that means if you wait for any b, okay, somewhere in between, positive but less than beta, there's a time, there's a length of interval, and if you wait long enough throughout an interval, after that interval, the Lyapunov, the solution passed through the Lyapunov function always stays under this border of B. Okay. Now let's prove this claim, and it will directly give us asymptotic stability. Because what? Define minus gamma as max. X belongs to omega beta and v of x greater than or equal to b. Okay. Omega beta was the intersection of r ball and v of x less than or equal to beta. Okay, and then we're now intersecting it furthermore with v of x greater than or equal to b, and b is something smaller than beta. Okay. And we're interested in maximum value of this function b dot. Okay. Now since the x greater than or equal to b guarantees that x is far away, maybe not far away, but there's well, some distance far away from the origin, b dot is always negative in that closed and bounded set. Okay, therefore this maximization is achieved with some negative number, and that negative number we're indicating by minus gamma. Okay, because minus gamma is negative, gamma has to be a positive number. Okay, so by therefore 3. Gamma has to be a positive number, positive constant. Okay. Syntax. Now define T as beta minus B over gamma. Then v of x of t less than or equal to b, where t is capital T. For otherwise, v of x of t would be b. Okay, so this doesn't hold, means that v of x of capital T is greater than or equal to x would be greater than b. But if this is strictly greater than b, the whole solution must be strictly greater than b for t from 0 to capital T, because v is strictly decreasing. Why? Because v that is negative. V that is negative, okay, along the solutions. For all t in 0 to t. And okay, this implies that v dot is greater than or equal to minus, or excuse me, less than or equal to minus gamma. Okay. And v dot x of t less than or equal to minus gamma for t in 0 to capital T. Okay. We can write now, in the light of our discoveries, the following: v of x of t equals v of x of 0 plus from 0 to t integral of v dot x tau e tau. Okay. Now v of x of 0 is less than or equal to beta. Why? Because we start from the delta hole, and if we start from the delta hole, automatically we are in omega beta. That's what we have shown. And if you're in omega beta, that means initially v of x of 0 is less than or equal to beta. And then what else? This thing. Okay, since in this interval from 0 to capital T, v of xt is larger than b, v dot is less than or equal to minus gamma, because this is the maximum that's attained by v dot. Therefore, this is less than or equal to minus gamma. Okay. And this whole thing, v of x of capital T, therefore must be less than or equal to beta minus gamma times the length of interval, which is t. And this, by definition of capital T, is no other than b. Okay. Hence, we reach a contradiction. Okay. Okay. Okay, because here, suppose that, okay, so the contradiction is such that this is, after our argument, we reach this, and this means that at t equals capital T, v of x of capital T is larger than b. Now, we have obtained that v of x of capital T cannot be larger than b, so that's the contradiction. And if we have v of x of t is less than or equal to b, and since v dot is never positive, that means for all future times, and now by future times we mean times further than capital T, it has to remain below b. Okay. And v dot greater than 0 implies v of x of t less than or equal to b for all t greater than or equal to capital T. Therefore, our claim holds. Okay. No matter what b you choose between 0 and beta, you can always find time that's large enough so that if you wait throughout that time interval, the x of t eventually goes down the b line. Okay, and now let's see what the claim implies. The claim implies that if you start from initial condition such that norm of x0 is less than equal to delta v of x of t should converge to 0. And why is that? Because consider, for instance, here some v. Okay. This is v of x of t, and here this is the t-axis. So, initial condition less than or equal to delta means that v of x of 0 is less than or equal to beta, and v of x, okay, we start from, let's say, this point, this is beta. V of x will always remain below that line, okay, because set omega beta was forward invariant. And then we choose any b. Suppose that that b is beta over 2. Okay, 1/2 beta. That means that corresponds, we can find a t, let's call it t1, and after t1, we will always, v of x of t will always remain below that line. Okay. And then choose now 1/2, 1/4 beta. Then we can find some t2, which would be larger than t1. And after t2, v of x of t will be below that line. Okay, so that means this is forbidden region, this is forbidden region, and so on. So v of x of t will always be pushed further and further toward the 0. Therefore, something like this must happen. And eventually, v of x of t should converge to 0. Okay? And that convergence of the Lyapunov function to 0 implies that the state or the norm of the state converges to 0. Why is that? It's because since the solution bounded, that is x of t less than or equal to epsilon for all t positive, okay, and b is continuous by assumption and positive definite. We have to have v of x of t converging to 0 implies x of t converging to 0. So the situation is something like this. This is x, v of x. Okay, so something like that. It's 0 only at 0, and in some vicinity the origin, let's call this epsilon. So the state always have to remain in some bounded neighborhood of the origin. Okay, and in this closed bounded set, v of x has to decrease further and further, and it cannot decrease anywhere except 0. Okay, therefore x of t has to go to 0. Hence, x equals 0 is asymptotically stable, and that marks the end of arguably the most important theorem in stability theory.